For this last problem, we're going to be doing some probability review. So if you remember stuff from 70, or if you took data 140, 126, etc., hopefully this is a quick refresher. If not, then hopefully this is comprehensive enough for you to do on the course. Okay, and so given that A, B, and C are some events, and I define here the complement of A, or aka like the opposite of A. Let's say like wearing red shoes, the complement would be like not wearing red shoes. So I define that with a little bar here. And so the first rule is the complement rule. So the probability of A happening and the probability of A not happening, well, that covers all possibilities. So the sum should be 1. For rule 2, we have the probability of A given B. And so the probability of A given B is equivalent to, well, we're given the event B. So we can say we're like dividing over like the overall probability of event B happening. And so given we already know that the event B happens, what's the probability of A also happening when B has happened? And so you can logically say, well, that's equivalent to the probability of A and B over the probability of just B happening. And so this part actually comes from part 3. So part 2 was called conditional probability. Now we're going to be talking about Bayes' rule. And so Bayes' rule says that the probability of A happening and B happening is equivalent to the probability of B happening times the probability of A happening given B has already happened. And this is equivalent to the probability of A happening and the probability of B happening given A happened. So in all 3 of these scenarios, you end up having both like event A and event B happening. And so logically that makes sense as well. And so given we know this relation, probability of A and B is equivalent to this, now we can apply it in our conditional probability rule by saying this equal to that. And that can often be helpful in our problems. Okay, and so the 4th probability rule here is called the total probability rule. And so total is a hint. So let's say you just want to know the probability of event A happening. Let's say my event A is that I go out today wearing this brown sweater. And so, well, the probability of me walking out with a brown sweater is equivalent to the probability of me walking out with the brown sweater given I wear my first pair of shoes times the probability I actually wear that pair of shoes, plus the probability that I wear this brown sweater given I wear my second pair of shoes, times the probability I actually wear that pair of shoes. And so let's say I pair my sweater with every single possible pair of shoes. If you sum up all of those probabilities, you should get the overall probability of me just walking out with a brown sweater, right? Because it doesn't really matter which shoes I wear. And so that's the total probability. We can condense this summation into this notation right over here. Okay, and the last 2 rules here we have are related to independence. So if event A and event B are independent, then the probability of A and B happening is just the probability of A happening times the probability of B happening. And for rule 6 is if A and B are conditionally independent, given some event C, then the probability of A and B, this comma is also like equivalent to like and. So the probability of A and B happening given event C is equivalent to probability of A given C times the probability of B given C. And there are definitely more probabilities or properties, a lot more properties out there. And if you run into a property that you're unsure of, just search it up and hopefully the internet will provide a good resource. Okay. Now let's move on to the actual question. And so starting with 3A. So for context, an incoming email is spam with prior, the probability of S is equal to 0.2 and the probability of this email not being spam equal to 0.8. And now we have 2 independent filters flagging spam. And so here we're given some conditional probabilities, like the probability that the first filter flags something as spam, given that we actually did receive spam, is 0.9, and the probability that the first filter marks it as spam given we didn't receive spam is 0.1. And so here's some very useful values. And we're told that F1 and F2, the filters, are independent given the class of whether it's spam or not spam. So this hints to us something related to conditional independence. Cool. And so now we're asking, what is the probability that both filters flag an email as spam? And so just writing this out, right? How would we turn this English into some mathematical statement? Well, the probability, or actually, why don't we first define? So F1 is a filter, and it's 1 if it thinks spam, 0 if thinks not spam, not spam. And we have literally like carbon replica almost for filter 2, but it's a different filter and they are independent. And overall, we have two states, right? We could either, and this is just an arbitrary variable, I'm probably not going to use it. You can look at the discussion solutions if you want to see how they use it, but you can think of it as we have two cases, right? Either the actual mail is spam or the actual mail is not spam. And so these are all the possible scenarios we can have. And so the probability that both filters flag an email as spam. To write this down, we can think of it as the probability that both F1 and F2 are both equal to 1. So they both have flagged this piece of email as spam. What does that mean? Well, if both filters flag something as spam, do we actually know whether the mail that came in was spam or not? We don't. So we need to consider both. So this is where the law of total probability comes in. A quick reminder that the law of total probability is that given we know some event, we can sum it up with all the possible sub-events times the probability of that sub-event actually happening. And so over here, we can write this as the probability that both filters marked it as spam, given that this piece of mail was spam. So we multiply it by the probability that it was spam, and we add this to the case in which, again, both filters flagged it as spam, but this time we know that the mail that came in wasn't actually spam, so given it wasn't actually spam. Alrighty, and so further simplifying, for each of these ones, we were told right over here that F1 and F2 are independent given the class S or S conjugate. So what that means is we can further split this with the conditional independence rule right over here, number 6. We can simplify this to be equal to probability of F1 equals 1 given S times probability of F2 equals 1 given S times probability of S. So that is I'll start it. So this is like the first little equation, and then we add it to the second half, which is probability of F1 equals 1 given S conjugate times probability of F2 equals 1 given S conjugate times probability of S conjugate. And so for some clarification, this part corresponds to here. This highlighted green corresponds to right over here. Here, probability of S corresponds to that probability of S, and this corresponds to that. Wonderful. Okay, and so now we can actually start plugging in numbers. The probability of F1 is equal to 1, so aka it thinks it's spam given S is 0.9, so it's right over there. And I'm going to plug in the rest of the values. So over here we have 0.8. Over here, the probability of S is 0.2. And we add this to the probability of filter 1 thinking it's spam given that the mail wasn't actually spam, which is 0.1. And then this here is 0.05. And the probability of S conjugate is 0.8. And so if you calculate this, we'll get 0.144 plus 0.004. And this gives us a final probability of 0.148. So the probability that both filters flag an email as spam is 0.148. We don't care, we don't know what the email actually was. All we know is the fact that both filters flagged it as spam. Great. So moving on to part B, it says, given that both filters flag an email, what is the probability of the email being spam? Again, we should always start by turning the English words into an equation. And so you can think of these words as given that we know that the both filters have flagged an email. So they have flagged this email. Oops, not to nowhere. Okay, both filters have flagged this email. What is the probability that the email actually was spam? So they were both flagged, but is it actually spam? That's our question. And so we actually do end up using, I guess, C over here. So C represents whether something is equal to S or S conjugate. And so here we set C is equal to S. So what is the probability that this piece of mail was actually spam, given that it was flagged? And so when you see this kind of given, right, we're given that both filters flagged an email. We want to know the probability that it was spam. Whenever you see that, you should think of Bayes' rule. And so in Bayes' rule, we can turn this equation, because this is, we can't really calculate this on our own, but we have calculated other values that we can now use to our advantage. So a quick reminder of Bayes' rule is probability of A given B is equivalent to probability of actually, you know what? This is a little bit complicated. Let me just show you the actual thing and it makes sense. So we have the probability of F1 equals 1, F2 equals 1, and S times the probability of S over the probability of F1 equals 1, F2 equals 2. Okay, now I'm going to show you how this corresponds to Bayes' rule. So if you think of this as probability of A given B, right, so this whole thing is B. Probability of A given B is equivalent to the probability of B given A times the probability of A over probability of B. And the more you use this rule, the better you'll get at it. But you can see over here, this is B, this is A, this is also A, this whole thing is event B. Okay, so I'm going to erase the correspondences now that we have used Bayes' rule. Now we want to solve for the actual values. And actually, lucky for us, we've solved most of these values. So the probability that both filters mark something as spam, given we think it's spam, right? So given S times the probability of S, this is what we actually calculated when we calculated the total probability rule here. And so this value is 0.144. And the probability that F1 equals 1, and oh, this should also be 1. Oops. And F2 also equals to 1. So the probability that both of them have marked it as spam, well, that's actually what we calculated in this original problem, right? Was the probability that both filters flag an email as spam, and we found it to be 0.148. So this is 0.148. And if you finally solve for this, you'll get approximately 0.973. Okay. If this part was confusing at all, or if this part was confusing at all it really was an application of the total probability rule and the conditional probability combined with Bayes' rule right here. So here. And so I encourage you to review that if you are still a little bit stuck. With practice, it will get easier. Otherwise, thank you for watching and congrats on finishing discussion 1.